You're listening to the Common Descent Podcast. Hello, Will.
Hello, David.
Hello, listeners, and welcome to episode 103 of the Common Descent Podcast. Today's topic is the Paleocene-Eocene thermal maximum.
Woo!
The PETM to its friends.
Yeah, that's much more convenient.
It's a much shorter. It is a very complicated, big words sort of title that is actually very self-explanatory.
Mm-hmm.
This is an event in Earth's history that occurred at the border between the Paleocene and Eocene epochs about 56 million years ago. And what makes the event an event is that there was a lot of heat.
Yeah, thermal maximum.
Thermal maximum. It got real warm, real fast, geologically speaking, which had all sorts of interesting impacts on the world around it and interesting implications for any scientists interested in studying what happens when the globe gets particularly warm in a particularly short amount of time.
Yeah, hypothetically, of course.
Just in case that was ever of interest to anybody.
In some sci-fi situation where the world was heating up at an inordinate rate due to some highly evolved invasive species.
Right.
We would like to know.
Right, especially if carbon was involved.
Yes.
But that's enough speculation. In this episode, we're going to talk about what the PETM was, sort of the world that led up to it, what exactly happened, what that rapid climate change looked like, why we study it, what sort of studies have gone into it, and then, of course, the most fun part of these discussions, what happened as a result.
What did it do?
What did it do to the world? Because it did some fairly fun stuff. This is one of the most famous events in Earth history that isn't a mass extinction.
Yeah.
Which is not to say that there wasn't extinction.
Oh, yeah, anytime there's change.
There was. But this isn't one of the big five, but it is, I have seen it called the largest natural climate change event of the Cenozoic Era.
Wow.
So we'll talk about that. Hey, another reason why it's fun to talk about the PETM is because it was requested.
It was?
It sure was, by Rita, Ivana, James, and Connell.
Cool. Thanks for the request.
Good idea. It was fun to do some background research, and it'll be fun to talk about.
This is one of those topics where I'm ready to learn because I know about this topic.
And I'm ready to teach. Before we get into it, just a couple of announcements. Announcement number 1, we have a Patreon.
We do.
Patrons who Patreon with us will get all sorts of goodies, like bonus audios, like we did a cool live stream recently. We might do more of those in the future. And if you're a patron at a certain level, we'll say your name in gratitude on the podcast. This episode, we would like to gratitudify Mike, Amy, Sam, Cindy, and Robert.
Thank you so much, everyone.
Welcome to Patreon. Thank you for supporting us. And thanks, as always, to all of our patrons and all of our listeners. Speaking of special things, our end-of-the-year Q&A is coming up.
It is.
We took lots and lots of questions from lots and lots of people for this year's end-of-the-year Q&A. So keep an eye out. On December 31st, we will release the official Q&A, in which we will answer as many questions as we get to in the time that we have, because we got so many questions.
We got a lot of questions this year, which is fantastic and awesome.
Excellent.
But also keeping things realistic. Yeah, we're going to have to do as much as we can.
So we'll spend a number of hours answering questions until we run out of time.
Yes.
Thanks, as of course, to everybody who submitted questions. We hope that you will have as much fun listening to the Q&A as we have doing those Q&As. And finally, our last announcement, and indeed the last announcement of the year, is that it's the end of the year.
It is.
Happy holidays to everybody. Happy New Year to everybody. Thanks for sticking with us through 2020. And after this episode, we look forward to seeing everyone in 2021.
Absolutely. Here's to the next year. We'll see you all there.
And speaking of things that are new and changing and news, let's talk about the news. Before we get to our main topic, every episode we like to pick some news from the world of paleontology, evolution, things that we are interested in and that interest our listeners to keep everybody up to date. Will, why don't you kick off the news?
Cool. My first news is about the fact that we may finally know what group of animals pterosaurs came from.
Oh, I remember hearing about this.
Yeah, this is pretty exciting. So pterosaurs, big flying reptiles, sometimes big flying reptiles.
Big deal flying
Big
reptiles.
deal flying reptiles.
Big enough for a whole episode 79.
Yes.
That supersized episode, actually.
Yeah, exactly. In the Mesozoic, have been a evolutionary mystery for the fact that we don't have a good early record of this group.
Right.
Very similar to bats, the first pterosaurs we find look like pterosaurs, so we don't have a good transitional fossil record, which means we don't really know how they evolved flight or who they evolved from, what group of animals they evolved from. We know that they're in archosaurs with dinosaurs and crocs, but it's been heavily debated where they fall out in that group. Exactly. This research suggests a group that might, if not be their ancestors, close relatives of their ancestors.
Oh boy, oh boy.
This is research by Martin Ezcura et al. In Nature, and the article we'll be linking to is by Laura Gagel in Live Science. So as I was saying, pterosaur evolutionary history has been a bit mysterious and heavily debated and just lacking a lot of the evidence needed to clear up that mystery. This research is actually not on like a new species found. It's a group we've known since the 70s at least, which are a group of small reptiles known as the Largopetids, which lived about 230-210 million years ago.
Okay.
And were thought to be likely relatives of dinosaurs because their hind limbs and pelvises resembled or were closely resembling dinosaur back legs and pelvises, hips. But this is research on a more complete Largopetid fossil that shows more of the skeleton and shows some features that brought that into question and is what led them to the potential connection with pterosaurs. The particular specimen they were looking at was a small animal. They said it was lightly built and likely bipedal, so two-legged, walking on its back legs.
Yeah. One of that abundance of small, thin, two-legged reptiles running around in the Triassic, from which the dinosaurs and relatives eventually emerged.
Yeah, exactly. It looks a lot like that overall body shape. It has short forearms, forelimbs. They were able to micro-CT scan the specimen, the fossil, and analyze the brain case. And they found some interesting features there. A number of aspects of the brain case suggest that this Largopetid had a similar shaped brain in certain ways to pterosaurs, particularly the inner ears. And so the inner ears, if you ever remember your intro anatomy classes or just general biology stuff, are those loops that are inside our inner ear that are full of fluid that can help our body maintain balance and tell whether we're sideways, right side up, if we're moving, what direction we're moving. This is what makes you dizzy.
Very handy for active, mobile animals.
Exactly. So analyzing inner ears of animals can often give you an idea of how they're moving, how much they're moving, or what importance there is in their movement. If you have large inner ear, typically that means you're a more mobile in 3D space animal.
Right. Climbing, flying, things like that.
Leaping and stuff. And flight is about as 3D as you can get.
Yep.
So very characteristic inner ears for flying pterosaurs. These Largopetids show similar inner ear structures. Now, they do not think that Largopetids are necessarily the ancestors to pterosaurs, but that they are likely a sister group to the branching, where pterosaurs branched from their ancestors. Largopetids would be on the other branch.
Right. So they are relatives of the ancestors of pterosaurs.
So whether or not this is what the ancestor of pterosaurs looked like, we don't know, but this shared inner ear feature could suggest that that is an ancestral trait, which could mean that pterosaurs got some of their adaptations for flight before they were flying.
Right.
That big inner ear might have been something they were using in a different lifestyle before it was used for navigation while flying. But of course, there are some big questions still left open in the fact that this Largopetid looks nothing like a pterosaur. It's long back legs, short front legs, which is the opposite of what you need to be a pterosaur. And it does not have the extremely elongated neck or face or anyway, so it does not look like a pterosaur on the outside, but on the inside there are some key features.
Interesting.
So this is definitely not a nail in the coffin on the debate for where pterosaurs came from, but it seems that logopedids might be less dinosaur cousins, more pterosaur cousins, which may get us a step further into figuring out where they came from.
Yeah, that whole Triassic early Archosaur mess has been difficult to sort out. And so as we slowly kind of separate the branches and figure out the real evolutionary patterns within there, it helps us isolate which of those early things were actually more like dinosaurs, which ones are more like pterosaurs. What I really like that this is an inner ear connection.
Yeah.
Because that's also how it happened with whales.
Yep.
That the earliest fossil whales were originally recognized as whale relatives, despite having bodies completely unlike whales by features of the inner ear.
Yeah.
That were shared with true whales later on.
Well, there's those moments in evolutionary history where groups develop really weird extreme body types quickly, so that unless you just happen to have a really good fossil record during that time, you won't be able to just by a glance go, well, obviously those are related. It's like, well, no, because now we're flying. And we weren't doing that a relatively short amount of time ago. So those internal structures can become really important clues.
Yeah. Cool stuff.
Yeah.
Well, on the subject of new insights into early evolution of cool animals, my first bit of news is about snakes.
I knew it.
I don't get to do a lot of snakes in the news. They're not in the news nearly as much as some other pretender.
As the survey winners.
This research specifically reports on multiple specimens of what is now the oldest known python.
Cool.
Cool stuff indeed. This is research in Biology Letters by Hussam Zaher and Krister Smith, and we will link in the blog post, all the news stuff gets links in the blog posts, to a press release on phys.org via the Senckenberg Museum. The snake fossils in question are, we're so used to hearing about the oldest of something, or snakes in particular, as very isolated pieces of skeletons.
Mm-hmm.
But this is from the Messelpit of Germany, which means it's real good. 4 nearly complete skeletons of this species, each one with at least a partial skull.
Wow.
So a real good find. Each one, the snakes appear to have been about 1 meter long, right? 3 feet, which is a decent size, I suppose.
Yeah, it's not a tiny snake.
From the Messelpit of Germany, as I said, which is a famous site for its extremely good preservation. It's a UNESCO World Heritage Site, I believe.
Right.
Dating to about 47 million years ago, the Eocene. These specimens were named as a new genus and species, Mesolopython freyi, Mesolopython,
Yep.
and freyi named after Eberhard Frey, who is known for doing studies on living and fossil reptiles. This snake is named in honor of that scientist. This discovery is intriguing for a number of reasons. Number 1, because they're the oldest known pythons. The next oldest pythons come from the late Oligocene to early Miocene, so quite some time later, in Australia. And what's really notable about that is that pythons today are found much farther south.
Mm-hmm.
They're found in southern Asia, in Africa, they're found in Australia. So if you look at those older fossils, those other fossils, plus where their living species are, you might get the idea that pythons basically have a southern evolutionary history.
Yeah, that they started there and they've remained there.
That they are a Gondwanan, right? The southern continents. But this species is from Germany, which is northern. That is Laurasian.
That's not in Australia at all.
That's sure not even close. Which is interesting because a northern origin has also been suggested for 2 close cousins of pythons, the Loxocemus group and the Xenopeltis group.
Mm-hmm.
So this might be pointing us towards not only did those python cousins first evolve in the north, pythons also may have first evolved in northern continents and then spread to their current distribution. Another thing that's interesting, and this is another biogeographical note, is that this fossil site also contains Eoconstrictor, one of the oldest members of the boas, which we talked about in episode 84. I don't know that off the top of my head. I know that because I remembered looking at it, and so I searched our blog. Check out our blog. I was like, we've definitely talked about Eoconstrictor. Where was it? That's right, episode 84.
Nice.
I don't know all the news.
No.
This is interesting because boas and pythons are two different branches of the snake family tree. They evolved independently, even though they're very similar. Mm-hmm. They live in similar environments. They have similar body shapes. They have heat-sensing pits that are similar to each other. But modern distribution, pythons are Old World, boas are New World, and in the fossil record, they're also separated, which has led people to reasonably suggest that these two snake groups may have evolved in total isolation from each other. Mm-hmm. But here at the Messel site, we have at least one species of each. This is a case way early on, Eocene, where pythons and boas lived alongside each other.
Wow, Messel pit's just messing up all of our preconceptions.
It really is just making a huge, throwing a big wrench in our whole snake evolutionary history timeline.
I love it.
Yeah. Snakes are one of those groups that are so diverse and so widespread and so ancient compared to, things like mammal groups that are a bit more recent, that it can be very difficult sometimes, especially if you don't have a good fossil record, to really nail down where exactly did you get started.
Well, they also have the similar issue that a lot of croc evolutionary studies have, where there's a lot of convergence.
Yes.
Not to say all snakes look the same because they're long and skinny, but
pythons and boas, for example,
you could put. I've been in places where they are housed, in two habitats next to each other, and if the labels weren't there, it's that's a big snake that squeezes stuff, and that's a big snake that squeezes stuff.
Yep, they both live in the tropics. Yep. They both have little legs in the back. Yep.
Very, very similar lifestyles, anatomies, and so it can be, that can muddy the waters even more if you're having to go off of pure anatomy, if those anatomies have converged.
Yeah.
So yeah, it can get really confusing, and stuff like this makes it even more interesting when it's they may not even started where we thought they started.
Which can be a big help in telling us where to look. Because if it turns out that their origin is in Europe, then everybody looking for the oldest pythons in Australia is going to come up short.
They're going to have a rough time of it.
It's not going to go well.
Very cool. Well, speaking of rewriting fossil stories based on new evidence, this is research on what was thought to be a dinosaur, an example of a dinosaur Pompeii, which we've mentioned before, but may be evidence of burrowing.
Ooh.
Maybe a different reason it was preserved so well.
Man, I gotta say, 100 episodes in, we've gotten real good at these news segues.
Right. This is research by Elaine Chen et al. And was presented at the meeting of the American Geophysical Union, AGU. So it is not published yet, but it was reported on because it was presented. The article is by Mindy Weisberger in Live Science. So Cretaceous Pompeii is a phrase some of you might have heard, and we've mentioned, I don't remember which one where we mentioned it on, is often a reference to a site in China called the Liaoning province, which has a number of very well-preserved fossils, ridiculously 3D, sometimes soft tissue preserved dinosaur and other animal fossils.
Yeah, a lot of the really famous dinosaur, bird, all sorts of finds recently from China are from various fossil sites across Liaoning.
Yeah, feathers and stuff like that as well. Coloration comes from, a lot of findings about coloration comes from the site, from this region. This research was on two psittacosaurs, Psittacosaurus being a member of this group. This is Psittacosaurus lujatenensis, which is the parrot-faced dinosaur.
These are early members of the ceratopsian group, the Triceratops and friends.
A little, if you know Protoceratops, picture that a little bit. It's got a similar beaked face.
Yeah, short beak face, a little spikes on the cheeks. No horns, not yet, and bipedal, or at least partially bipedal.
Yeah. So
not very much like Triceratops.
No. But this research is on two specimens of this species that were preserved in this region. and had been, thought to be preserved in that Pompeii-like effect where the pyroclastic flow, the ash flow coming off a volcano, can basically freeze and flash preserve living organisms.
Right, like an avalanche of ash and stuff, just burying all the things around it.
This preservation can also be caused by something called a lahar, which is a similar flow but with mud mixed in.
Yeah, it's a volcanic mud flow.
Yeah. And these things can rapidly and in high detail preserve living organisms. So a lot of these dinosaurs have been pointed to as evidence of a similar Pompeii-like event in the Cretaceous. These two specimens, though, they took a closer look at and found some interesting evidence. They extracted sediment grains from the rock structure surrounding the skeletons and within the bones of the skeletons. They analyzed it for zircon minerals, which we've talked about, to determine exactly how old the sediment grains are.
Yep, zircon's great for dating.
And they found that many particles around the skeleton were quite old, dating to 250 million years to 2.5 billion years old.
But both of which are much older than Psittacosaurus.
Yes. And that's the point they made. The sediment of the region is 125 million years old. And this proportion of older grains, of those very old grains, was much higher with these two specimens than with other fossils that do seem like they were definitely buried by the pyroclastic flow. Which means that the idea that these were also trapped that way seems a little less plausible, a little less likely.
They're buried in different sediments.
Exactly. That they were buried in a different way than the others by older sediments. And what the researchers proposed is that something like a flowing river could very easily carry old sediments into an area. And if these animals were in a burrow and a flood filled their burrow with old sediments from somewhere else, that would also preserve them in a very similar way to the the Pompeii preserved specimens, which may mean that these were burrowing psittacosaurs, which was not something proposed for this group before this research.
Nope.
So this may be evidence for a burrowing behavior, or at least a burrow living, squatting behavior. Maybe they didn't dig them, but that they seem like they were underground very likely.
Yeah.
To be preserved this way with the sediments that they're preserved in.
Interesting. This is not the first suggestion of burrowing dinosaurs. There is I can't think of the names.
Changminia leongnensis was the sleeping dinosaurs that were...
That's right.
Seemed like they were sleeping in a burrow. They were curled up in a sleeping position and preserved in the Liaoning province again. So yeah, this is not the first example of...
Yeah, and I can think of another one. I can't think of the name. But yeah, there have been suggestions of burrowing in dinosaurs, or either digging their own burrows, or finding burrows of other things and going in there, which wouldn't surprise me. There are a lot of small dinosaurs that would benefit from being underground.
Well, and there's tons of animals that do that. I don't know how common knowledge that is, but there's lots of snakes that live in burrows that don't dig the burrows. Rattlesnakes are not burrowers, but...
No. But when gopher tortoises dig a burrow, snakes will go in there and hang out.
That's a normal part of their behavior and a key to their survival. So dinosaurs could absolutely be living in burrows that they may or may not have dug themselves.
Yeah. And burrows are nice because it's you've chosen a tomb.
Yes, exactly. It keeps you safe a lot of the time, and then when it doesn't, it's real nice for us.
It keeps your skeleton safe. Well, speaking of animals tucking themselves away to stay safe,
nice.
My next bit of news is about signs of possible hibernation in a group of ancient animals that we didn't know hibernated. Humans.
Oh.
Right?
I mean, I hibernate all the time. They should have just said.
And then your mom knocks on the door and you have to get up.
Yeah, the school's been closed for a little while now. I've been hibernating for a few days.
This is research by Antonis Bartschokis and Juan Luis Arzuaga in the journal L'Anthropologie, and we'll link to an article in Science Alert by Jacinta Bowler. The evidence in this case comes from a cave in Spain known as Cima de los Huesos, which is a very famous site for hominin fossils, ancient human relatives, dating to a little over 400,000 years old. The hominin remains in this cave are thought to either be early Neanderthals or ancestors of Neanderthals. Thousands of specimens have been found from this cave. This study took a sample of those bones and examined them for signs of diseases, including, they CT scanned them, they looked at histology, which is the bone tissue patterns, and they found lots of damage on bones, lots of lesions and things that fit issues like hyperparathyroidism or rickets that are signs of chronic kidney disease.
Okay.
That some of these specimens had symptoms that were affecting their bones that might be linked to chronic kidney disease, which is interesting because we see those kinds of issues show up in animals that hibernate, particularly if they don't have enough fat stores to survive the hibernation.
Yeah, their body runs out of food while they're sleeping the winter away.
Right.
And starts to break itself down.
And if you didn't quite have enough food to make it the whole winter, you start to develop some of these issues. So if you're hibernating, like a lot of mammals today hibernate, there are reptiles that brumate, which is the same basic idea. You go into a deep sleep and you wait for a few months until it gets warm again and you can come back out.
Yeah, hibernation, you'll often hear the phrase suspended animation used. Torpor. It is not just that you're sleeping through the winter, it's that you shut down, to where if I just went in and tried to rock you awake, it wouldn't be like waking up from a really good sleep.
Right.
It's your body is in sleep mode.
Yeah. Yes. You're in stasis a bit.
And yeah, for a time so that you're not wasting energy and you can live off your fat, hopefully, until the weather outside gets better.
They also found evidence of vitamin D deficiency, which is something you see in organisms that are not getting enough sunlight.
Yeah, when you're sitting in a cave.
And they found evidence of growth in the bones varying season by season. So they suggested that, I think particularly for the younger, young adult hominins in this case, that they were experiencing seasonal growth spurts. Their growth was disrupted year after year.
Yeah.
Which is what you would see if you were spending a few months not eating anything.
Yep, not eating, not moving, not doing much.
So all this evidence together, they're suggesting we might be seeing signs of these hominins hunkering down in a cave for a few months and not moving, which would fit with the idea that they were living, the known idea, that they were living during an extreme glacial period.
Yeah.
That the winter may have been particularly difficult, so it was beneficial to just tuck yourself away and wait for spring. Now, if that's true, it would be quite a surprise. I believe there are primates that hibernate or do something similar to hibernation, but it's not known for humans.
Nope.
We don't do it. We don't have the ability to do it. If you tried to do it, you would just waste away.
Yes, because once again, this isn't just that I'm gonna tuck in with Netflix for a long time. Your body physiologically goes into a different metabolism.
Right. If you try, your body can't do that, and if you tried to just sleep for 3 months, you wouldn't wake up.
Yeah, you would eat all your fat way too quickly and die.
Now, there have been suggestions, of course, that they may be wrong about this. Right? There are people, I read this article, and this article references an article in The Guardian that has some people expressing caution. One of the cautionary responses is there could be other explanations for these kinds of diseases. One note that one of the people cited makes is that hominins might not have been capable of hibernating.
Yeah.
Because we as animals tend to have particularly high energy requirements, notably for our giant supercomputer brains. That needs a lot of energy. And one person referenced in the Guardian article sounds like they're basically saying, well, we don't know if a hominin brain could survive not getting any energy that long.
That an anatomy so similar to our own could be adapted to hibernate like that.
Right. So, future research on this is probably going to include, more looking at anatomy, but also genetic studies.
Mm-hmm.
Because if there is the capability of hibernation in this lineage, we might be able to see genetic signals of that kind of physiology in Neanderthals or Denisovans or possibly even our own ancestors. Which is very cool because it can tell us a lot about our evolution, how we were living, what we were doing. But also, if our ancestors had this ability, then why don't we have that ability?
Yeah, where did it go, or why did we lose it?
So this is one of those amazing if true.
Yes.
Big if true.
Well, and it's because there's a lot of maybes, with if these diseases are a result of the chronic kidney disease, then it's solid evidence. But if there are other causes for these symptoms,
The Guardian article said that the paper said that in that same cave, there's evidence of a hibernating bear. But I could not get access to the full article. So I tried to look for that and I couldn't get into the article. So I don't know if that's true. Like, I couldn't find what they're referring to.
Yeah, what indicated it was a hibernating bear.
So there may be other fossil evidence from the same region that can help corroborate it.
Yeah. And so if those symptoms are symptomatic of a hibernation lifestyle, then it's good evidence. But if there's other things that could cause similar symptoms, then that is one potential answer, but may not be the only one. And the other thing I keep thinking of is, of all the animals, we have real weird complex behavior.
That's true.
That could behavior be allowing them to do something that gives symptoms of hibernation, but they're not actually hibernating? Is it just, all right, everyone, it's just wintry terribleness outside. We're rationing. It's hardtack, Neanderthal hardtack.
Gruel. For
the next 3 months. Don't move around much. Like, we're just hunkering down. Could that also impede growth spurts? Could that... so it's... how many answers are there for these symptoms?
Now, the abstract of the paper does say that they examined a lot of alternatives. But again, I could not get access to the paper, so publish your papers in open access journals and then I can talk about them. Well, anyway, speaking of segues, let's wrap up the news and move on to our main topic, the Paleocene-Eocene thermal maximum.
When you didn't need to hibernate.
Right. Where there was no hibernation, there were no hominins. It was just a very different world. After the break. As I mentioned earlier, the Paleocene-Eocene thermal maximum is an extreme climate event that happens at the boundary between the Paleocene and Eocene epochs. But before you can have the boundary at the end of the Paleocene, you have to have the Paleocene. So let's set the stage. Notably, before you have the Paleocene, you have the beginning of the Paleocene. The Paleocene is the first epoch of the Cenozoic Era, which means it comes right after the Mesozoic Era, which ended with a bang.
Yes.
Well, it ended with a bang and a whimper. A bang followed by a lot of whimpering.
Yeah. I feel like most things that ends with bangs are followed.
That's probably true. Unless it's a real big bang.
Yes.
The Mesozoic ends with the end Cretaceous mass extinction event. Asteroid impact, also maybe other stuff happening. Go check out episode 5, which marks the end of the Age of Dinosaurs, one of the biggest mass extinctions in Earth history. The Paleocene, coming immediately after that, is in many ways a world in recovery. The Paleocene sees the start of the Cenozoic Era, the Age of Mammals, starting 66 million years ago and running towards 56 million years ago. So let's set the scene. This is the world during the Paleocene. Geographically speaking, Pangaea had already begun to split up during the Mesozoic. So during the Paleocene, the southern continents are rather spread out, while the northern continents still have a lot of lingering connections. Mm-hmm. Over the course of the epoch, we see the North Atlantic begin to open. The northern continents continue to spread out. The Rockies are on the rise, literally, in North America. The Indian Plate is beginning its grand union with the rest of Asia.
its impact.
Climate-wise, the Paleocene is a very warm time. Kind of similar to the Cretaceous before it. Significantly warmer than today. A time with no polar ice caps, as far as we can tell. This was a, quote, greenhouse world, as opposed to an ice house world. There were either no polar ice or very little polar ice, and we have evidence of polar forests.
Yes.
So, warm, rich world, somewhat diminished in diversity at the beginning, despite its rich climate.
And when we say polar ice, that means like year-round ice.
Right, like Antarctica.
That doesn't mean that in winter it didn't freeze at all, but that...
There was still snow.
Yeah, but that there was not an ice cap of just, yep, there's ice here and this is where it lives.
Life of the Paleozoic involves a number of exciting radiations. Notably, birds. Modern groups of birds appear and start to radiate, including the Paleocene is famous for a lot of early penguins.
Woo!
As well as the first true giant flightless birds like Gastornis, plus bunches of other groups. There are some real impressive reptiles known from the Paleocene, including Carbonemys, one of the biggest turtles of all time, Titanoboa, one of the best reptiles ever. There were also some crocs, I guess.
There were bunches of crocs.
But the thing that the Paleocene is probably most famous for in terms of life is mammals. This is the start of the age of mammals. And so over the course of the Paleocene, we start to see early signs of a lot of familiar animal groups.
Yeah, now that the mammals are out from under the heel of their dinosaur overlords, they can rise up.
There are a number of extinct groups that do pretty well during this time. The rodent-like multituberculates, the hoofed condylarths, which are relatives of our modern hoofed mammals. We see early cousins of groups like primates, hoofed mammals, xenarthrans, things like that. And then in the late Paleocene, we start to see a number of these groups achieve something that will become a big deal for mammals, which is large body size. We start to see the first bigger mammals, big herbivores in groups like pantodonts and uintatheres, big carnivores like the mesonychids, starting to get extinct groups with diversity, with larger sizes. The age of mammals is beginning.
Yeah, the Cenozoic did not start with mammals taking over right away. They took some time still being the smaller preyed upon groups as birds got big and terrestrial crocs and stuff tried to take over the predator roles, but eventually mammals started filling the niches in the environment that we're used to seeing them today.
And then, at the end of the Paleocene, we see a couple of particularly famous things happen with life of the Paleocene. One is we see a famous turnover of mammals. That is, Paleocene-style mammals are replaced by Eocene, the next epoch, style mammals, which includes the first appearances of a lot of familiar groups of mammals, like early primates and early hoofed mammals like perissodactyls.
Yeah.
And, for a long time, people have known that not only was there this big change in mammals, there was also a change in ocean microorganisms, specifically benthic foraminifera. We've talked about foraminifera before. These are plankton, right? Microorganisms that have little shells that live in the oceans that are super famous for being useful for studying all manner of environmental things from the past. Benthic forams are the ones that live on the sea floor, often deeper ocean. Benthic forams experience a mass extinction at the end of the Paleocene.
Weird.
Now, paleontologists and geologists knew something happened at this time because we get this big change in mammals, we get this something happened with some of these ocean creatures. Those changes, it's not a coincidence that those changes happen at the boundary because that's often how we identify boundaries is changes in life.
That's why we've labeled it a boundary.
Yep. But it wasn't until relatively recently that we started to realize what happened at that boundary. We now know that what happened is that the climate changed dramatically. The Paleocene-Eocene thermal maximum, named because it happens on the border between the Paleocene and Eocene, is an event called a hyperthermal.
Nice.
Which is science speak for real hot.
Yep.
Dated to about 56 million years ago. Specifically, one recent paper I saw cited dates of 55.93 to 55.71.
Wow.
We've gotten there's been a lot of study on this. It's not the...
It's the events of this thermal maximum take place between...
Yes. It's not the only hyperthermal. Even of this time, there were hyperthermal events before this and hyperthermal events after this. But this one is famous for being rather extreme. Studies over the last few decades have found evidence of global temperature rise of an estimated 5 to 8 degrees Celsius that rose and fell all within the span of probably less than 200,000 years. So a geologic blip that just big rise in temperature. Now,
wow.
For comparison, 5 to 8 degrees change. The difference between the peak of the last glacial maximum, where half of North America looked like Antarctica, versus today is about 4 degrees Celsius.
Yeah.
If I remember correctly. This was a rise of more than that. Temperatures went up, fell back down in a relatively short period of time, and the world was different afterwards.
Yeah.
As I said, it has been, I've read it described as the largest natural climate change event of the Cenozoic Era, of the last 66 million years. It is the most famous climate change event of the entire Cenozoic Era, except, of course, for the one that we're doing.
Yup.
Like I said, early on, we knew there were changes in the ocean. We knew that land ecosystems had reacted. But the early signs of the PETM, the early evidence of this event, started showing up, it seems, around the early 90s in the form of evidence from oxygen and carbon isotopes.
Okay.
Chemical evidence began to give away the existence of this event. Oxygen isotope evidence can be used to indicate temperature records. So, oxygen is an element on the periodic table. Isotopes are different forms of the same element of atom. The two most common oxygen isotopes that are relevant to this kind of study are oxygen-16 and oxygen-18, which differ in their atomic mass, so their weight is different. That weight difference is part of the reason you can use oxygen isotopes to infer ancient temperatures. For example, when temperatures rise and you have lots of evaporation, water that evaporates into water vapor is contributing oxygen to the atmosphere, but that process happens more readily with lighter molecules than with heavier molecules. Mm-hmm. So if a lot of the oxygen moving up into the atmosphere and through your cycle is happening because of evaporation, it can be a sign that things are getting warmer. That's a relatively simple explanation of that relationship, but measuring the difference in ratio between lighter versus heavier oxygen can give you a sense of what the temperature was doing in the atmosphere and in the ocean. Oxygen isotopes for this time period have been examined in plankton shells, because of course they're building their shells out of things like calcium carbonate and whatnot, which have oxygen in them. Fish scales, mammal teeth, all of these are animals collecting oxygen from their environment. So if you have a certain temperature affecting the oxygen composition in the environment, those animals are picking that up and preserving that same ratio. This was some of the early signs of a temperature shift at the Paleocene-Eocene boundary. Since then, there have been other studies of temperature. There have also been studies that look at leaf margins. So leaves of plants will be different. They tend to be smoother in warmer climates and spikier margins of the leaves in cooler areas, which has to do with transpiration, with releasing water.
Yeah, water loss and retention.
And there's a very popularly used method called TEX86, which looks at the remains of lipids in the cells of certain ocean microorganisms. And the structure of those molecules depends on temperature.
Oh.
So you can examine the structure of those biomolecules to get a sense of the temperature.
That's nifty.
All of this evidence since the early studies has pointed us at this conclusion of a rise in temperature at this time of around 5 to 8 degrees Celsius. A couple of studies that I looked at cited measurements of sea surface temperature of around 35 degrees Celsius in some places. One source that I read said that during the PETM, some middle latitude or even polar regions might have been warmer than modern-day tropics.
Wow.
Big change.
Real hot.
Now, this isn't like the warmest that the Earth has ever been, but what's significant is that it was a rapid shift from what it had been before to a big rise of several degrees in temperature. A global average rise of 5 to 8 degrees can have some really dramatic effects. Like I said, peak of the last ice age to now is several degrees. The temperature change that climate scientists are worried about these days is a few degrees. The other major evidence of change that goes back to some of these early studies are changes in carbon isotopes. And whereas the oxygen isotopes are one of our proxies for temperature change, carbon isotopes are one of the evidences that tell us about why the temperature changed.
Yes.
Just like oxygen has multiple isotopes, so too does carbon. Typically, we're looking at carbon-12 versus carbon-13, which are stable isotopes, as opposed to radioactive carbon-14. The ratio of different carbon isotopes in the atmosphere, in the ocean, can be affected by changes to the carbon cycle. One of the earliest big deal signs that something had really gone haywire at the Paleocene-Eocene boundary was an excursion in the carbon isotopes, a rise in the ratio of lighter carbon versus heavier carbon, which is typically affiliated with a major influx of carbon into the atmosphere. You tend to see that kind of change when lots more carbon is being contributed to the atmosphere due to a shift in the carbon cycle. This, of course, is relevant because carbon tends to enter the atmosphere in the form of carbon dioxide or methane, which are greenhouse gases.
Yep.
When carbon-rich greenhouse gases go into the atmosphere, they trap heat, which tends to lead to temperature rise. This isn't like we know because of this one event. We see that correlation between rising carbon in the atmosphere and rising temperatures over and over again through history. We see it now. It's also laboratory experiments confirm this relationship. It's one of the basic concepts of atmospheric science.
Yes, like this is something we've not only seen over and over and over, but has been directly tested in a multitude of ways. Like, yeah, this is just one of the fundamental facts about the way our atmosphere works.
Like with the oxygen isotopes, this changing carbon isotope ratio at the PETM has been measured from mammal teeth, from oceanic shells, which, same thing, are picking up carbon from the environment.
You are what you inhale.
You can also look at carbon-rich minerals. So as they're being formed or deposited in these surroundings, they're picking up that ratio. Altogether, pointing at not only was there a major temperature change at this period, but a major change in carbon in the atmosphere. There have been a number of different estimates as to just how much additional carbon was being rapidly injected into the atmosphere, and among the sources that I was reading in preparation for this episode, they tend to express this injection of carbon in measures like petagrams, which is, if I remember my conversion correctly, a petagram is 1 quadrillion grams, conveniently equivalent to 1 gigaton, which is 1 billion tons.
Nice.
The amount of rising mass of carbon in the atmosphere and following that the oceans during this time is typically estimated in some number of thousands of gigatons of carbon over the onset of the PETM. Big spike in carbon in the atmosphere and oceans, big spike in temperature. So as we alluded to earlier, you might start to get the sense of why scientists are so interested in understanding what happened during this time period. A number of the studies that I looked over make the point that the amount of carbon rise in the atmosphere at this time is estimated to be not dissimilar from the projected amount of carbon rise in the atmosphere from our current activities. Now, there are a bunch of open questions about this. We know their temperature rose, we know environments changed, we know that carbon rose in the atmosphere, but there are a number of questions that are still actively researched today, including how fast did that rise in carbon and temperature happen?
Yes.
Among the studies that I have looked over, I've seen a number of studies cite estimates of up to 20,000 years, perhaps lower at 10,000 years. I've seen some suggest less than that. There seems to be a general consensus that it was several thousand years or so during which this rise happened. There have been a couple of studies that have found evidence to suggest multiple pulses of carbon release into the atmosphere. So it might not have been one gradual event. It may have been two or more pulses. But overall, geologically, a relatively fast increase. Which leads to the next question, which is how long did it take to recover from that?
Yeah.
This is another thing that has been studied quite a bit, is eventually everything went back to, quote, normal.
Yes.
So
too reasonable.
Similar to what it was before in terms of both temperature and carbon levels in the atmosphere and oceans. As the natural processes that draw carbon out of oceans and atmospheres, like weathering processes, like plants taking in carbon, things like that, gradually brought things back to what they were before. Most estimates suggest that the entire ordeal, from start of rising temperatures to things going relatively back to normal, happened in about 200,000 years, maybe less. So geologically speaking, a relatively short-lived event.
Yeah.
Quick rise and then gradual return.
Yeah, that's geologically pretty fast.
When you look at the graphs of measuring carbon levels or measuring oxygen isotopes and temperature, it appears as a blip.
Yeah, it's very steep, up, down. It's not showing it as a slope.
Right.
Because that's how quickly it happened in reference to the scale of the Cenozoic.
And then, of course, there's the big question, which is, where'd all that carbon come from?
Yeah.
Didn't come from nowhere. Something must have happened to release that amount of carbon to be injected into the atmosphere. There are a number of candidates. One that I see come up a lot, and indeed this is the one that I had in my head, that I had heard about before, which are methane hydrates. You may also have heard the term methane clathrates. These are compounds of methane and water. So methane is CH4, carbon plus hydrogen, a big deal greenhouse gas.
Yep.
Methane combines with water to create these compounds that I've seen described as sort of icy, that are abundant in certain ocean sediments. These sediments can be a reservoir of carbon because they've got all this methane sort of locked in there.
Yeah, trapped.
But those sediments are stable under lower temperatures. So if they are exposed to higher temperatures, a change in ocean circulation, carrying warm water to them, or tectonic activity that can move where they are, a disturbance can cause those sediments to start to fall apart, which can release that methane into the ocean and then the atmosphere. Another similar candidate for a source of all that carbon rise is permafrost. Like we said, there weren't permanent ice caps at the time, but you still had cold areas and you could still have had frozen soils, permafrost.
Yes. Yeah, that's different than standing ice.
Yes. Frozen soils can also contain lots of organic matter. You can have peat or, plant remains, things like that. So permafrost can also contain lots of carbon-rich compounds within those soils.
Yeah, things that haven't been allowed to rot fully and release those things.
So These are two potential sources that, if disturbed, could start releasing lots of carbon into the atmosphere, both of which are also commonly talked about in reference to modern climate change, because both of those also serve as strong feedback sources. Both permafrost and methane-rich sediments can release their carbon store when exposed to higher temperatures. They melt, basically.
Yep.
So if things start to get warmer, because these things are being released, it can create more and more of that release.
Let's say you get a little bit warmer, you release some of your gases, which creates a bit more greenhouse gases, which heats up things a little bit more, which melts you further, which releases even more, and then
positive feedback loop, which is something people are worried could be very negative today.
Yep.
Another source of all that carbon that I've seen suggested in a number of places is wildfires.
Oh, yeah.
Because living things, plants, are also a carbon source, a storage of carbon. Plants are full of carbon, and when you burn them, that smoke is releasing lots of carbon material into the air. So if you have areas turning drier, they could be exposed to the potential of fires. If you have, I saw one source reference drying out of inland seas could end up exposing a lot of organic material. If tectonic activity could potentially uplift old coal seams, which could then end up being burned. The wildfires hypothesis is one that I've explicitly seen disputed.
Yeah.
I think I saw one paper that was looking at, we should see XYZ evidence if that was the case, and we didn't see it in our study. So it's a potential that has been suggested. I don't know if it's one of the top candidates.
It does seem like it'd have to be a lot of wildfires to be a main cause.
So it sounds like hydrates and permafrost seem to be more commonly brought up as plausible explanations. And then, of course, there's the other main candidate, the other one that seems, from what I've seen, to be a top candidate. And at this point, it's like having a running. If we were on TV, we'd be like, "All right, audience, say it with us."
Yep.
Large igneous province volcanism.
Yep. I've been waiting for volcanoes.
Volcanic activity.
Yep.
Today, right, in the normal process today and forever of the carbon cycle on Earth, volcanoes are one of the major ways that carbon is transferred from within the crust back up into the atmosphere.
While the wildfires make sense, uncontrolled burning of organic materials is not good for the environment, I've heard. But to cause such an extreme spike over such a short time globally, like to that, in that way, seems like a tall order for fires.
Yeah.
But volcanoes those are events that can affect the globe. Like one volcano can have far-reaching effects for years by itself.
Yeah. And
a bunch of volcanoes can affect the globe.
And as we've discussed in every extinction episode, large igneous province volcanism is large-scale, long-lasting volcanic activity that creates an igneous province, a region of igneous rocks produced over time by all of this extrusion of lava. And where you have extrusion of lava, you have gases coming out.
Yeah, it's bringing things trapped down in the earth up. It's causing chemical reactions with all that heat as it's interacting with stuff on the surface. It's just belching forth chemicals that were quietly happy.
Yeah, not only do volcanic gases are often full of carbon-rich materials, but the lava can contact sediments that are full. Right? You can have sediments that have a bunch of carbon or methane within them. You can have coal seams, melting those and releasing that additional carbon.
It's also a good way to start fires.
In this case, the igneous province in question is the North Atlantic Igneous Province, which is a region centered on Iceland, and you can study some of it on the surface in Iceland. These eruptions are known to have happened between roughly the early Paleocene to early Eocene, but had their peak of activity around the Paleocene-Eocene boundary. So this, of course, has also been pointed at. Yeah, this volcanic activity could be contributing to the rise in carbon materials in the atmosphere. And then, of course, it won't surprise anybody to know that I found one study. It might not be the only study, but I found one from 2016 that presents evidence of impact material
Heyo!
from around this time. So glassy spherules that the type you get when an asteroid impacts the planet. And as we discussed in our KPG episode, episode 5, if an asteroid crashes into carbon-rich sediments, it can also release a lot of carbon material up into the atmosphere. So there's a lot of possible sources of all this carbon. Like I said, the top candidates that I have seen discussed more often, I'm not an expert, seem to be volcanic activity and then those carbon-rich sediments, permafrost or methane hydrates. Interestingly enough, you can try to distinguish between these different sources by examining the rate of rise of carbon, as well as the carbon isotope ratios will look different from different sources. So volcanic carbon could potentially have a different isotope ratio than what you might see from, I don't know, wildfires or something like that.
Interesting.
Yeah.
That can be handy.
And then, of course, I'm going to say the answer could be, but realistically the answer is almost certainly some combination of multiple sources, considering that more than half of the things we just listed are triggered by heat.
Yes.
If you have volcanic activity that starts to cause rising temperatures, that can lead to melting permafrost, it could lead to more wildfires, so there could easily be a lot of interplay between different potential causes.
Yeah, you can have one event kick off the beginning of another, and then you get that feedback loop going.
Yeah, and like I said, there have been some studies that have suggested multiple pulses of carbon release, which could easily be one thing started it and another thing picked it up and continued the trend afterwards.
Yeah, so it's as is very typical when we talk about geological events and Earth history events. There's almost never, and here's the one smoking gun. It's
in this case a literal smoking gun.
Yes, geological events like this, extinctions, crazy climate changes are much more like the death of Caesar than they are a sniper taking someone out. It's not just, and this one thing screwed up the environment. It's like, no, all these things with their knives did a little bit enough to set up a incredible event.
So we know major temperature shift, several degrees, just ridiculous amounts of carbon injected into the atmosphere, throwing off the carbon cycle, creating that rise in temperature, sourced from some number of different places around the planet, which, of course, as you can expect, caused a variety of environmental effects. So after the break, we'll talk about some of the side effects of the Paleocene-Eocene thermal maximum.
Well, I hope they're all good.
The PETM was a time of dramatic change, which impacted ecosystems all over the planet. Now, you might be thinking, well, temperatures got warmer, isn't that good for things? And the answer is, yeah, some things.
Yeah.
Not all the changes are necessarily negative, but that could be said for almost any. Even a mass extinction, the scavengers and the decomposers are having a field day.
Oh, well, and it's always easy to focus on the bad things when a big change happens, but hey, when we invented ships, rats did great.
Oh, yeah. So there were a lot of rapid changes. Let's start with a bad one. In fact, the most famous bad one, benthic foraminifera, suffered a mass extinction. Like I said before, these are microorganisms, little shelled, often single-celled microorganisms, specifically sea-floor-dwelling ones. Estimates have suggested that at this boundary, during the PETM, they lost between 30 and 50% of their diversity. That's a big deal extinction. During the PETM, studies have found species of benthic forams being generally smaller and with thinner shells.
Oh.
Now, this seems to be the only group that we have evidence of a big deal extinction event, but there's other evidence to suggest that the deep sea especially was hit pretty hard during this event. There's evidence for low oxygen, right? Anoxia, which can result from temperature changes. It can result from shifts to currents in the ocean carrying nutrients to different places.
Yeah, hot water typically holds less oxygen.
Yep. We also see evidence of ocean acidification.
Yep.
Which is what happens when lots of carbon dioxide ends up entering into the ocean, chemically interfering with ocean chemistry.
Yes, it makes it harder for things that build shells to build them. It's not that it's acidifying and melting the shells. It interrupts their chemical process to build.
Yeah. It's basically chemical reactions are happening in the water that is taking away carbon from being available to build shells.
It's getting trapped in a new cycle because there's too much carbon.
So thinner shells on your forams could easily be as a result of less available carbon, or that you're just unhealthy because there's low oxygen, there's low nutrients. We do see effects in other groups of ocean organisms. Planktic forams are the ones floating around higher in the water column. We see a lot of changes in where they're living. We see changes in size. Some of them get bigger, some of them get smaller. There are certain studies that have found areas where warm water algae move in and replace cooler water species.
Yeah.
One study I was reading referenced a particularly interesting case of a group of dinoflagellates. So these are, again, unicellular, eukaryotic microorganisms that live in the ocean that build little shells around themselves, which means that they fossilize great. These are an important component of plankton in the oceans. I learned about them, I think, originally from my Magic School Bus computer games back when I was a kid.
Yep.
One group of dinoflagellates, Apectodinium, in the Paleocene are known from low latitudes, so, near the equator, tropical zones. During the PETM, they show up everywhere, up to the poles.
Wow.
In some sites, they end up being almost half of the fossils you get of marine organisms. This group did real well, which makes me kind of imagine this the equivalent of algal blooms everywhere.
Yes.
Of this particular type of plankton. And then, of course, given all this talk about oxygen shifts and ocean acidification, it will not surprise anybody, I assume, to hear that I have seen multiple sources reference that coral reefs did not do well during the PETM.
Nope.
Just like they're not doing well today, that carbon cycle disturbance messes with corals' ability to build their skeletons.
Yeah, their calciferous skeletons. And this is a really great example of, it seems counterintuitive because corals are tropical.
Yes.
Warmer weather should be great for coral. You should be able to make coral reefs up in Maine now.
And indeed, warm, temperature?
Yeah.
Not a problem.
But
to a point.
Sudden, quick rise in carbon dioxide that's creating that warm temperature has other side effects other than just the temperature.
Yes.
And so you can have groups that hypothetically should be doing great with the temperature, but aren't due to the chemistry.
And that's a trend that we're going to see as I continue talking about these effects. They're not all straightforward. Really, even though what happened was relatively straightforward, more carbon, more temperature, the effects are varied.
Yes.
We see this as we move on to land environments. There is lots of evidence of changes to precipitation, both regional areas but also globally, changes in precipitation. And you might think, it gets warmer, so things get drier.
Yeah.
Less precipitation. Or you might think it gets warmer, so there's more evaporation.
More clouds.
More moisture in the air, so more precipitation.
But both of these make sense.
And they both happened. In different places.
Yes.
So there have been a lot of studies that have found that some areas seem to have gotten more humid during the PETM, while others got drier. I saw one study that, I think this was the same study that looked at one site in India and one site in Spain, and found evidence of increasing wetland environment in the Indian site and increasing arid environment in the Spain site. Different places reacted differently. There's also evidence of changes in runoff. So when it rains, rain carries sediments, down from highlands, down from the land, and that sediment accumulates in lowland basins or in, lakes and stuff.
Mm-hmm.
And you can look at that sediment accumulation to get a sense of what was the pattern of rainfall and runoff. And there's evidence to suggest that it wasn't necessarily that there was now more rain or less rain, but that it was different.
Yes.
I've seen studies reference evidence of seasonal variation, so that the seasons became more dramatic. So you had more of a dry season and more of a wet season. And or that you had more intense storms.
Yeah.
So during your wet season, you're even wetter because you're having more intense rainfall during the storm season. So we're seeing a variety of impacts to ecosystems around, not only in the oceans, but also on land.
Yeah, this makes me think of those times where you get not even ridiculously heavy rains, but just a good rain in very dry places can be devastating because the soil's not prepared for it.
Right.
There's not grass and trees holding it together, so that's when you get mudslides and...
all that runoff, all that sediment is carried away.
Yeah.
As you might expect, we see some intriguing changes in plants.
Oh, I bet.
At this time. Now, a lot of the studies that have been done on the PETM have actually happened in Wyoming, in the Bighorn Basin, which covers this time period. And there's been some intriguing study of plants and animals in that region. I haven't found any references to particularly widespread extinction in plants, but there was a bunch of reorganization. Studies of the Bighorn Basin in Wyoming have found that during the PETM, conifers disappeared from the region, right? This is your pines and spruces just weren't there.
Wow.
And the plants in the area became dominated by the legume family, relatives of beans and peas and stuff.
Huh.
Which today are particularly common in tropics and subtropics. And then, afterwards, it went back. After the PETM ended, the conifers came back and the beans left.
It's just they were on vacation.
Yeah,
They're
just took a little trip.
Visiting here.
But we also see reorganization of plants that didn't all reverse afterwards. So, for example, during the PETM, we see a lot of movement of plants between North America and Eurasia.
Now, so this was an opportunity for them to move, and then after they stayed where they were.
Yes, because there were connections between those northern continents, like I said, but it was cold up there.
Mm-hmm.
Even if it wasn't cold as today, still cold, and if you're a warm climate plant, you can't spread up there.
Yeah, and when it comes to land bridges, you can't move across the land bridge. You have to live across the land bridge.
Right. Which is really what happened. When we talk about land bridges, I think it invokes this idea of a little passage that things can... But typically when we're talking about those connections, we mean that there was a habitat.
Yes.
Up on that bridge, as we might call it.
Yeah, the only reason we call it a bridge is because it's not there now.
Right.
Otherwise, it would just be another part of those continents.
So when it got warmer, certain types of plants were able to spread into those northern areas, inhabit those areas between the continents, and end up spreading to another continent.
Yes.
So this event seemed to be an opportunity for plants to disperse between continents. And not all of them vanished. Some of them stuck around.
Yeah. Well, yeah, because in this case, it's not a situation where cold-adapted plants were pushed out of an area and warm plants moved in. It's just that, oh, hey, we can go over there now.
Yeah.
This
is now part of our range.
It's just that we've unlocked this passage, and now we can grow over there. We would have been fine growing over there before now. We just couldn't get there.
Yep. I also saw reference to a study from 2008, which I think was also in Wyoming, that found evidence that during the PETM, plant fossil leaves showed more insect feeding traces.
Oh.
Which they suggested could be either that higher temperatures means more insects, that they were just doing really well, but also high levels of carbon dioxide in the atmosphere can interfere with plants' abilities to create certain proteins.
Oh.
So it could be that the plants themselves were actually less nutritious because of the carbon-rich atmosphere, so insects had to eat more
Oh.
in order to get what they needed.
I wonder if it would also affect the plants, some of their defenses, like any chemical
maybe
defenses against insect feeding in, so they weren't, the insects could gorge more.
I don't know.
Oh, that's fascinating. I hadn't even thought of that.
And speaking of animals, once again, the most famous impact of the PETM is in mammals. This was the beginning of the age of mammals, and the PETM ended up being an important moment in the rise of mammals. Notably, at this time, we see mammals doing the same thing that the plants are doing, spreading between continents.
Yeah.
Those connections between North America and Eurasia allow groups to not only disperse, but also radiate, evolve. Around this time is when we start to see the first representatives of perissodactyls, right? Your horses, rhinos, tapir ancestors. Artiodactyls, the other hoofed animals that eventually would give rise to deer and cows and giraffes and such. Early primates, early carnivorans, the hyenodonts, which are not hyenas but a different group of carnivores. A lot of these mammal groups have their very early appearances around the PETM, which might be related to them getting to disperse into new areas and develop into new forms. I've even seen at least one source, I think this was a popular article, that suggested we might have the PETM to thank for modern diversity of mammals, that they got a kickstart during this time period.
That for whatever reason, it gave mammals what they were needing to become more what we see today.
Now, of course, that makes it sound like, oh, hooray, mammals did great. Well, no, new mammals took over for old mammals.
Oh, yes.
This was still bad news for somebody. I also have seen references to lizards dispersing to new places, and some early appearances in certain groups of turtles around this time. It wasn't just mammals doing brand new things. But one of the most famous things that mammals did during the PETM is also, I think, the strangest and most wonderful part of this story. Mammals shrunk during the PETM.
Yep.
They were smaller. There was a study in 2012, which I've seen referenced a whole bunch, that looked at an early horse genus named Cypherhippus. Before the PETM, the researchers looked at teeth to estimate body size. Average body size for these horses is estimated to have been around 5.5 kilograms, 12 pounds. Early horses, very small creatures.
Yep.
12 pounds. So that's like a small but not tiny dog.
Yeah.
During the PETM, average body size seems to have been 4 kilograms, or 8.5 pounds. So very tiny dog.
Yeah.
House cat.
Yeah.
That's a decrease of about 30% in average body size, and then afterwards they return to larger sizes.
Yes.
This trend has also been seen in other hoofed mammals, in early carnivores, in primates. Mammals got smaller during this event. This is not unique to the PETM. We've seen this in other hyperthermals. There was I've seen studies of Eocene climate heat spikes, warming periods, that also see some degree of shrinkage. It's been noted that since the last glacial maximum, some of our modern mammal groups have gotten smaller. Certain rodents and certain hoofed mammals have had a decrease in their average body size as temperatures have risen. There are a couple of reasons why this could be. One is that it could be the same principle as Bergmann's rule.
Yep.
Bergmann's rule is the general principle that many mammals follow, that the higher latitude you're at and the colder it is, the bigger your body is.
Yeah.
Because among mammals produce their own heat. So if you have a big body, you tend to lose heat more slowly. So shrinking your body size improves your surface area to volume ratio.
Yep.
Surface area dictates how much heat you lose. Volume dictates how much heat you contain.
Yeah.
So smaller animals lose heat more efficiently, more quickly than bigger animals. So as it gets warmer, it might just have been more comfortable, right? Better off being smaller to reduce that heat.
Well, I love this mechanism of evolution because it's one of those where it is not adapting to like a task, where like any group of animals can get big. Mm-hmm. Like we've had giant members of just about every group. And so that is just a matter of adapting a body to get big. But temperature is a physics problem.
Yes.
That is a thermal regulation problem. And physics doesn't really care about a lot of that anatomy stuff. It works the same way for every situation, and physics does not scale 1-to-1. So if you have higher temperatures, smaller sizes are going to be more efficient.
Yeah, regardless of what kind of animal.
Exactly.
Right. Many lineages of mammals experience this shift.
Yeah.
Another feature that really doesn't matter who you are is how much energy you're getting from your food. And like I mentioned with the insect feeding, if plants were struggling at this time, if they weren't producing their normal proteins because of high carbon dioxide levels, or just it got drier where you are, and so you have less plants able to survive in your region or whatever, that means less food.
Yes. Less
food for herbivores, and if there's less herbivores, there's less carnivores. So it could be that the bottom of the food chain was less productive. Mm-hmm. There was less energy and food to be found in your plants at this time, which could also be one of the reasons why mammals got smaller at this time. Just because you couldn't be big in some places.
Yeah, you could subsist on less food if you're smaller, while a big elephant needs pounds of food or it will starve.
And then the PETM ended after, 200,000 years or so, and the mammals got bigger.
Yeah.
And then, in fact, continued to get bigger as mammal evolution progressed.
Yes.
So I think that horse study found that that they were average of 5.5 kilograms before, average of 4 kilograms during, and then I think they went up to 7 in the early Eocene, which might be some sort of great rebound, but it could also just be horses over time showed a trend in many lineages of getting bigger. So
exactly.
That doesn't necessarily mean that they rubber banded back up. They could have just gone back on their trajectory that they were already on.
Yeah.
So the PETM, it's this wonderful, because like when we talk about extinctions, there's, all right, and everything died, and here's a list of what died, and here's a list of the things that died a little less than the other things. Yes. But this was an event where absolutely certain things got bad, and then other things got better in some ways. Mm-hmm. Plants and animals were able to disperse. That one dinoflagellate group just had a field day.
Yeah.
And then there were other effects that were just kind of weird.
Yeah, that just changed things.
Rain got weird. Mammals got smaller during it. It really is a great indication of how that kind of shift to your Earth system just kind of alters everything. Some for bad, some for better. Just kind of throws a wrench into the entire global system, which brings us to the reason why the Paleocene-Eocene thermal maximum is so intensely studied today.
Yep.
Because it is a time period where massive amounts of carbon entering the atmosphere caused intense climate change over a short period of time that had global impacts of varying degrees. There are few events in Earth's history that are as tailored to our needs today as this event. Like I said earlier, there have been estimates of how much carbon was moving into the atmosphere and oceans at this time that are similar to some of the estimates of what we might be looking forward to with our modern anthropogenic climate change. So the PETM is a great opportunity for us to look, okay, well, what happened the last time that this very similar thing happened?
Yes.
Which brings us to the paleontology side of studying climate. This is a great example of the benefit of paleontology and climate studies, is that the Earth history is just a laboratory of case studies. What happens when climate changes? What can cause climate to change? One of the reasons why so many scientists are intent on studying modern climate change, one of the reasons why it's become such a big, important, kind of frightening deal, is that we have all that record from the past that tells us this kind of thing happens in the past, and A, things tend to change dramatically, and B, what's happening now is not the same.
Yeah.
We don't have large igneous province volcanism going on. We don't have big reservoirs of permafrost or wildfires intensifying more than what we've seen prior to this, intensifying to the degree that they could explain the rising carbon in the atmosphere and the rising temperatures we see today. What does explain it is human activity,
Yes.
burning of fossil fuels, pumping carbon dioxide into the atmosphere.
Yeah, it's that we know what events like this look like when they naturally happen. And this doesn't look like that.
Right.
The only thing that we can connect it to is our behavior.
Yes. So we have this intriguing parallel where we can compare what happened during the PETM when natural events, right, quote unquote, within your bounds of what you count as natural,
Yeah.
but non-human related events, because we weren't there, caused a climate spike, versus today, where very clearly human activity is linked to our rise in carbon and rise in temperature. So there have been a lot of studies examining these facets of that. Not only is the PETM an opportunity to investigate that change, but also the long-term impacts.
Mm-hmm.
Not just what happened in, that year, but in hundreds and thousands of years following that climate shift, following that rise in carbon in the atmosphere. Already, there have been studies of the PETM that match some of our predictions of what might start happening with our modern climate change, including changes to precipitation, like I said, intensifying storms, evidence of ocean acidification, evidence of plants and animals changing their ranges. This is something that we see happening today.
Yes.
In some regions where plants are moving to different latitudes or different altitudes, where crops are functioning differently. This event, I've also seen studies reference it as an opportunity to examine climate sensitivity. What does regional climate look like when it responds to a global shift? How quickly do we see climate responses? How resilient is the climate?
Yes.
Right. How resilient is the water cycle?
How stable is it really?
Right. How much change does it take over how long a period to cause some of these shifts? This event is also a good opportunity to study how feedbacks work. We mentioned earlier that there are positive feedbacks. Positive doesn't mean good. It means
increasing
in a direction. So like we said, permafrost causing carbon release is an example of a potential positive feedback. The more it melts, the more carbon, the higher temperatures, the more melting you get. There are also negative feedbacks we can examine, which the planet has a natural carbon cycle, part of which is drawing carbon back into the biosphere, back into the crust, through sedimentation in the ocean. Plants take in carbon dioxide. So an event in the past is a good opportunity for us to look at which of those carbon sinks is important, has been important in the past for drawing that carbon back down.
Yeah, which might be our ideal to focus on.
Yeah, but yeah, what can we expect to see happen? Who can we rely on the most?
Yes.
But then also, can that contribute to what our behavior is? So there have been a lot of studies on the PETM and other climate change events in the past trying to answer those questions. How fast do things change? What kind of changes do we see? How does it exacerbate the rising temperatures? And what processes counterbalance those changes? Of course, there are some differences.
Yep.
The PETM is not a one-to-one exact comparison. For example, the starting conditions are different. The Paleocene was a much warmer time than today.
Yes.
One of the most important differences is that there were no ice caps, which is a big deal in our modern climate change scenario, because ice is a big deal.
Yeah, the poles back then went from being fairly warm with no ice to being very warm with no ice.
Right.
And then back down to fairly warm with no ice.
So you wouldn't have seen like the big melting of glaciers and stuff. which means, for example, that during the Paleocene-Eocene thermal maximum temperature spike, you probably didn't see a whole lot of sea level rise.
Nope.
Some, right? Water expands
Yes.
In warmer temperatures, but the kinds of stuff we've seen since the last glacial maximum, or the kinds of sea level rise we're worried about today, we're not going to see that at the PETM, because the water to contribute to sea level rise is going to come from the ice caps, from glaciers, from fresh water trapped in ice. Ice can also be one of those positive feedback loops.
Yep.
Because of an effect called the albedo effect. Ice is very reflective, so it bounces sunlight back up off of it.
Which helps keep our planet cool.
Which can bounce heat back away. So the less ice you have, the less you're bouncing heat back, the more heat you're keeping.
And the more dark water is exposed, which absorbs heat.
Yes. So the geography of the planet is not quite the same. It's not a perfect one-to-one.
The ice also means that it's releasing fresh water into the saltwater oceans.
Yes.
Which is a big change in ocean chemistry.
It can affect ocean currents, nutrient availability. And another one of the big differences between the PETM and today is the pace.
Yeah.
Like I said, studies are still trying to nail down exactly how quickly did that onset of the PETM happen. How fast did those temperatures rise? How fast did the carbon levels rise? But most of the estimates that I've seen seem to suggest that it was probably several thousand years to see that rise. So 5 to 8 degrees of temperature rise over several thousand, maybe 10,000, maybe 20,000 years. For comparison, we in our modern period of rising temperatures have seen 1 degree Celsius of temperature rise in the last 150 years.
Yeah. Slightly more than a single long lifespan for one of us.
And the models that climate scientists keep producing suggest that we will see potentially another degree of rise in the coming century. So if you're doing the math here, that's degrees per centuries as opposed to degrees per millennia.
Yeah.
During the PETM.
It's much faster today.
Potentially a much more dramatic change, which can make it a little more ambiguous when trying to figure out what are those impacts going to be. Which brings me to the other, and possibly, very selfishly, most important difference between the PETM and today, and that is who stands to be affected by it.
Yes.
During the PETM, a lot of the impacts we're studying are on, okay, what did this do to animal ranges? What did this do to their size, right? How did this affect ecosystems and environments? Today, there is the additional complicating factor that there is a global society of humans. That those environmental changes can then impact what we do. Our culture, our society, our population. So the PETM is looked to as one of the really exciting examples of climate change in the past that really in many ways mirrors what we're seeing today.
Yes.
And can really inform what we might see into the future and thus help us figure out how to behave in light of imminent change to a point. It's not the only one that we have to study, and it's not going to give us all of the answers, because really what we're seeing today is unprecedented.
Yes.
In a lot of ways.
It is something that's somewhat unfathomable in how quickly it's happening and how it's being caused compared to geological events of the past.
Yeah.
So it's got a lot of unknowns still. And something that this makes me think of is a common response when talking about the current climate crisis is that, but ecosystems adapt. And looking at the PETM, you could see a similar line of logic that is like, well, yeah, things changed and some groups did badly, but for the most part, it got different and weird and then it went back to all right. But as you mentioned, we saw new groups of mammals become successful, but that means old groups had to stop being. And when we say that there's a climate crisis and that the ecosystem's in danger, it's not saying that all life is going to disappear. life will fill the space of the life that dies.
Yeah.
But a lot of life is going to die.
And that's one of the great things that is shown by the PETM is that the changes are... I think a lot of people have that in their head, that there is the climate is going to change today and it's just going to be doom and destruction.
Yeah.
Which isn't the case, but it is going to be change.
Yes.
And the PETM shows us a great example of, things changed. Some things got real bad. Corals suffered. Benthic forams suffered a bunch. Other things did okay. Some things weird happened. But the point is that the world after the PETM was different.
Vastly different.
Than the world before it. And the world during it was even more different. The differences happened in a lot of varying degrees, and different regions reacted differently, different life reacted differently. But it was change.
Mm-hmm.
And yes, it went back to kind of normal.
Yeah.
It took 200,000 years. So the PETM it's a fascinating interval of geologic history, of mammalian history, and the history of, everything. Really interesting event. It's fun to talk about an event that wasn't just a mass extinction.
Yes.
But an intriguing burst of change. And one that has a ton of implications for our current situation in our modern world. All that being said, that's the general overview of the PETM. Fascinating time period, and there's tons of research happening now. So there will certainly be more to say about it in the future. So I hope everybody had as much fun hearing about the PETM as I had learning about the PETM.
Yeah, as I did just now.
And before we wrap up and finish up the whole episode once and for all, we have a patron question.
Yeah.
One of the things that our patrons get on our Patreon when becoming our patrons is the opportunity to submit questions for us to answer at the end of our episodes. Today we have a patron question. Will, what is that patron question?
Our question is from Julian, who says, in a fictional situation where there was some kind of human-like organism living in the Cretaceous, would it be possible to identify a process like domestication or selective breeding in the fossil record?
Interesting question.
Very cool. I like this question.
So something evolves to be domesticating and selectively breeding in the Cretaceous.
Yeah, some human brain-ish,
right,
similar kind of intelligence to us.
My inclination is to say no. That because we talked about this in episode 27, domestication. It can be really hard to distinguish domestication from just evolution, business as usual in our fossil record. And I feel like oftentimes the signs of domestication in the fossils themselves are identifiable because we have the living domesticates to compare it to. We know what a dog looks like, and we know that it's a dog, and we know it's domesticated, so we can look for dog-like traits in wolves in the fossil record. I don't know if we would have that luxury with something from the Cretaceous if they were, domesticating little dinosaurs.
Yep.
Would we just see that as these are two different species of dinosaur?
Yeah, here's a slightly bigger one, and then here's a slightly smaller one.
Yeah.
Or would we be able to tell that something had gone on particularly weird to get them into that new morphology?
Yeah.
And especially because a lot of research on our history of domestication is genetic a lot of the time.
Also true.
Looking for those signs of domestication of these have been interbred more consistently, or they have a connection to our modern lineage. We can see that there are domestic cow genes in this bovine, and we wouldn't have that from the Cretaceous.
We wouldn't have DNA.
No, so we wouldn't be able to track, and that wouldn't be a guarantee, but we wouldn't be able to track this group that we thought was a different species is real similar genetically, right.
Or look at intense trends.
Yeah, exactly.
In their genetic evolution.
If there was, though, a human stand-in organism back then, and they were domesticating stuff, I'd assume we would find them in relation to each other.
That was going to be my next point.
Yeah.
Is we could look for that association, that if we are seeing them... one of the early signs of domestication that we look for with humans and other animals is burial practices.
Yep.
The oldest known domestic dog in the North America, I think, is one that is buried alongside a person.
Yep.
I think there's one like that in Greece.
Yeah.
One or both of those might be considered among the earliest domestic dogs because it's buried in a grave.
Mm-hmm.
So we could see if we knew something about the cultural practices or behavioral habits of this ancient domesticator,
Mm-hmm.
we might be able to look for association with their domesticates.
Yeah, so if we found them regularly together with things like that, if we...
They had a fossilized leash on them.
Yeah, exactly. I don't know that any art would survive that long, but if we had any art of them showing that these animals were part of their daily domestic lives and not a hunting target.
You could also look for... I'm thinking of like farming ants,
Mm-hmm.
which have kind of domesticated,
Yep.
kind of selectively bred their fungal food. It could be that you could end up with a selectively bred species that is only ever found
Exactly, yeah.
alongside the other one, which could be a clue that it has to be alongside that other species in order to survive.
And I could see that there may be traits that we could identify. Like, once we got one clue for domestication, there may be other traits that are like, all right, well, that actually makes a little more sense why this one seems to be less efficient at running. Or, you know, it doesn't seem to be as well adapted to wildlife survival as the other of its kind that it is surrounded by. So why was it... why did it have all these weird grab bag of features? And then if we find it in relation with these dino humans, we can go, oh, okay, well, now those are starting to look like domestication features. Yeah. We may never be able to confirm it, but those might help get the idea more solidly in mind.
Yeah. The thing that I wonder, because we only have one example of domestication, and it's us.
Yep.
And domestication via us happens real quick.
Yes, it does.
Over thousands of years, which we might just not get in the Cretaceous.
Well, and it might
we might not get that resolution of time.
And
it might be a blip.
That's a good point.
They might just show up. Yeah. We might not find anywhere in that transition.
How long were these humanish things around? How long were they?
Yeah. How widespread were they?
Because if they were global like us, and if they lasted for millions of years,
right?
If they have a society,
hey, they have their equivalent of chickens and dogs that are everywhere with them.
But then I'd also assume we'd find their flying cars and spaceships if they were around for that long.
So it's an intriguing question. But short answer, I don't think it'd be real hard.
It'd be real hard. And well, another way to look at it would be if an alien found our ancient remains, would they be able to tell we had domesticated things? And unless documents survived, it may be very hard for them not to just say, wow, they brought in wild animals. Yeah. You know?
And then they had them a bunch.
Weird.
Interesting question. Well, it's a fun hypothetical that lets us extrapolate based on what we know.
Mm-hmm. Mm-hmm.
So thanks, Julian, for that fun question. Thanks, everyone, for listening. Thanks to our patrons. Thanks to our requesters. Thank you to everyone who has been with us for the year 2020.
Yes, thanks for sticking it out through this year, everyone.
We are excited to have completed a whole other year. We're almost at our 4-year anniversary.
Yeah, we are.
Coming up at the end of January. We hope that everybody has had and continues to have a happy holiday season. We hope you have a happy new year. We hope that everyone is doing well. And we hope that you will join us again in the year 2021. Don't miss out on our end of the year Q&A, which we will be releasing just in time for the new year. If you want to hear us ramble about random topics and answer questions for some number of hours until we get too tired to do it anymore.
It's always a lot of fun, and I'm looking forward to this year.
We will see everybody for episode 104 next year. Goodbye for now.
Take care of yourselves.
Thanks for listening to the Common Descent podcast. You can follow us on Facebook, Twitter, YouTube, and check our WordPress blog for pictures and links after each episode. Huge thanks to our patrons whose support helps keep this podcast running and who get access to bonus goodies on Patreon. The song you're hearing is called On the Origin of Species by Protodome, which we found at ocremix.org. Thanks again for listening. We hope you'll join us next time.